Okay, this video is on lesson 6.6, which is radical expressions and functions. So now we're going to focus our attention on the radical function and basically everything to do with radicals, being domain and range, simplifying radicals, eventually solving radicals. That'll be the next lesson. But even like dividing and multiplying with radicals. So really today is everything radicals. So we'll start off with what you already know, and that is how to find the domain and range of radical functions. So we can go down over here and find the domain of this function. Remember that the domain is restricted to what makes the inside of the radical not negative. So remember, you just set that up as 2x minus 5 has to be greater than or equal to 0. By solving and adding 5 and adding 5 and getting 2x is greater than or equal to 5 and then dividing by 2, you'll find that the domain is greater than or equal to 5 over 2. So domain is x is greater than or equal to 5 over 2. And then range, by looking at the graph, you'll see that the square root starts at y equals 0, as most of our radicals do. So y is greater than or equal to 0, and that will serve as your domain and range. Now, I'm not going to do the second one. I feel like by now, hopefully you should remember how to do it, but if you want to do it, just for practice, you can. The domain should have come out to x is greater than or equal to negative 18 over 5, and the range is y is greater than or equal to 0. Now on to simplifying radicals. This is another thing in which you have been introduced to. We did this in Algebra 1, and I can't remember if we did it a little bit last semester, but you have done this in Algebra 1 where you are dealing with radicals that involve numbers as well as variables. Remember that you can take the square root of a number, no problem. So like the square root of 49 is 7. But then remember that to get variables out of the radical, because square roots technically have an index of 2, now you never really saw that before, but it's understood that a square root has an index of 2, just like a cube root has an index of 3, and fourth root and fifth root, and so on. This is going to tell you what you can take out. You can take them out in groups of 2s. Because the index is 2, I can take them out in groups of 2s. How many groups of 2s x's are there? Well, there's only 2 x's, so it's only one group of 2. So one group will come out. Y's, being that the exponent is 5, how many groups of 2 are there? Well, 2 groups of y's can come out, but there is one left over because it's an odd number. It's 5. There is one left over, so we leave that in the radical. With z's, because it's being 6, how many groups of 2 can I take out? It would be 3. And that would be simplifying a radical that involved numbers and variables. Now, where this becomes a little bit new is we only worked with square roots in Algebra 1. We never worked with higher order indices like cube roots. But the concept is the same. The indice or the index here is going to tell you how many can come out, and what the groups need to be to come out. And instead of taking the square root of this number, you're actually going to take the cube root of that number. So the cube root of 27, and you can use your calculator for this, cube root of negative 27 is negative 3. But now with the variables, they can only come out in groups of 3. So how many groups of 3 are in 7? Well, 2 groups of 3 are in 7, and there's one left over. So I'm going to create a radical over here for my leftovers. There is an x that's left over. Y's, because it's 3, how many groups of 3? Well, 1, and then there's no leftovers. Z, because Z doesn't even have 3, it can't even form a group to come out. So the z's don't even get to come out. So the two of them that are in there stay in there. And that would be simplifying a cube root. But you could go to any order or any indices. You could see here with number 5, this is a fifth root indice. So we can, it's the same concept now, but now they have to be groups of 5. And I have to take the, wrong one. I have to take the fifth root of negative 32. Again, you can use your calculator. The fifth root of negative 32 is negative 2. But now all of these variables can only come out in groups of 5. How many groups of 5 are in 6? Well, just 1. And I do have actually 1 left over. How many groups of 5 come out of 5 with g's? And that's 1, but there are no leftovers. And h, once again, like the z's in the previous one, can't even form a group to come out. So they have to stay in, the two of them. And that would be simplifying radicals that involve numbers as far as variables too. The second part here, well, I guess it's sort of the third part, but the second concept here is going to be how do we multiply with radicals and divide with radicals. So it seems complicated, but all this really means here is that if you have things that are multiplied, as long as the index is the same for both radicals, you can multiply what's inside the radicals. So because they're both nth roots, I can just multiply what's inside the radical together. So a can be multiplied times b under the same root. Same thing with division. If both of these have the same indices, same index, same root, then I can divide the a and b inside the roots under the same root. So what that means is, and we'll look at an example here. In the first example, first thing I have to do is because I have an nth root, or I have a fraction here, I have to change it to a root. And remember that the base, or not the base, the denominator is the index. So since this is 1/3, that's a third root of 27ab to the third times the third root of 5a4b. So now back to what I was saying. Because both of these have the same index in the root, the same root, I can actually just multiply what's inside the roots together under the same root. So 27 can multiply times 5, and that's 135. And a times a to the fourth is a to the fifth. And b to the third times b is b to the fourth. And I can put that all under the same root to simplify it. Okay. Now, one more thing that you'll have to sort of be aware of is what we just did in the previous section, is that now that it's a third root, I can actually, simplify all of these. Okay. Now, unfortunately, like the first few examples, the number here is not a perfect cube root, because we do have to worry about the cube root here. 135 is not a perfect cube root. So we have to do our prime factorization tree to simplify 135. Now, we already know, because from the previous one, we already know that 27 times 5 is 135. So we might as well just use 27 and 5. And then that breaks down into 9 and 3. And 9 breaks down into 3 and 3. Now here's the thing you got to remember. With square roots, we looked for pairs, right? Pairs came out. But because this is a cube root, you actually have to look for threes. I have to look for groups of 3 to come out. Just like with variables, I had to have them in groups of 3. When you do your prime factorization, groups of 3 come out, not groups of 2 like in square roots. So I do have a group of 3 threes, so the 3 will come out. That 5, I'll put it over here. This is for my leftovers. 3 comes out. A's, how many groups of 3 can come out of the A's? Well, just 1, and there's 2 left over. And then B's, well, just 1, and there's 1 left over. And that's how you, and just to sort of make this look nicer, I'll bring it over. There you go. And so this is the answer to that problem. Okay, so let me recap this. This is sort of the meat of this lesson here. Because, now first of all, I had to change this first part, and I'll just use the scissors. I just had to change this first part to a radical, but with 1/3 it becomes a third root of the 27ab to the third. Because these both have the same root, they're both cube roots, I can multiply what's on the inside into one root. Then once it's in one root, I just use the previous lesson, this stuff up here, to simplify it. So 135 broke down into 27 times 5. 27 was 9 and 3, and 9 was 3 and 3. And remember, for cube roots, you have to look for 3's. You mean like groups of 3, not literally 3's, but groups of 3 to actually come out. Okay, and then the variables are the same as before. So let's try another one. Again, just like the previous problem, I have a 1/2 here. I have a fraction exponent that I need to change. So this right here, because it's a 2, it is a second root, or actually a square root. So what this becomes is the 8 just stays on the outside, but then it becomes the square root of 54x to the 5th. And then the bottom is 4 square root of 3x to the 3rd. So we can do the same concept with division. Because these are both square roots, I can divide what's on the inside of these into one root. Even the coefficients can be divided. So 8 divided by 4 is 2, square root. 54 divided by 3 is 18. And then dividing exponents, 5, you remember you subtract when you're dividing exponents, so 5 minus 3 is x squared. And then all I have to do is simplify. 18 goes to 9 and 2, and 9 goes to 3 and 3. Because this is a square root, I only need to look for groups of 2. So the 3 is going to come out and join the 2. Remember, if there's something already out there, it just gets multiplied. So 3's would join the 2, which is 2 times 3, which is 6. And then the variable, how many pairs come out? Well, 1 pair comes out. And they're actually, the only thing that's left over, is this 2 that was left over from simplifying the radical. And that's it. Okay. Try one more here. So in this one, just like previous ones, the 1/2, I have to change that into a square root with an index of 2. So I have square root of 54x3y3 over, this changes into a square root as well, of 3xy2. Again, because they have the same root, I can divide everything in here from everything in here under the same root. So I don't have anything coefficients, so it's just the radical. 54 divided by 3, again, is 18. Had that in the last one. And then you subtract the exponents. 3 minus 1 is 2, and 3 minus 2 is 1. I then simplify the radical. 18, just like last time, was 9 and 2, and then 3 and 3. So these come out. The 2 is going to stay in. How many pairs of x's? Well, 1. Now the y can't even make a pair, so it doesn't get to come out. It stays on the inside. And just to make this pretty, I'm going to bring this over. And that would be that simplified. Okay. So the last sort of concepts here are going to be adding, subtracting, and multiplying and dividing with radicals. These are not going to include any variables in this piece here. So let's look at the next page. We did adding and subtracting and multiplying a little bit with radicals in Algebra 1. Mostly just adding and subtracting. And one of the things that you had to remember is when you're adding and subtracting radicals, they have to have the same index and radicand. So, I mean, they have to be the same square root in order to add them. And the radicand, which is the number inside the square root, has to be the same as well. Remember that, yes, these are both square roots, but in order to combine them, this number on the inside has to be the same as well. So what we did in Algebra 1 is, in order to get these to be the same so that I can add these, is you had to simplify. So your first thing to do here is to simplify, if I can write, simplify radicals first. Okay, so that's what we're going to do. We're going to take both these, and we can sort of do these simultaneously for one or one at a time. 32 is, we'll just do 4 and 8, it's fine, which is then 2 and 2, and this is 4 and 2, and this is 2 and 2. So this ends up being two groups of 2, so 2 times 2 is 4, so this becomes negative 3 plus 4 radical 2, because there is that 2 that's left over there. 98 is 49 and 2. You can do it however you want. And then 49 is 7 and 7. And 7 is a prime number, so we're done. 7. So a pair of 7s will come out. So this becomes, this is in parentheses, plus 6 plus 7 radical 2. That radical 2 comes from that 2 that was left unpaired. Once they have the same square root and the same thing inside the square root, so notice now they're both radical 2, you can actually combine them now. So I'm going to sort of shrink these a little bit so I have a little bit more room. I wrote a little bit too big here. And then I'm going to do this one too. So now, once I have enough, and once I have them in the same radical, now it's just a matter of combining like terms. And numbers are like terms, so negative 3 and 6 is 6, and then radicals are like terms. So think of 4 radical 2 and 7 radical 2 like 4x plus 7x. 4x plus 7x would be 11 radical 2. And that is simplified. Oh, I can't add. Negative 3 plus 6 is not 6. Negative 3 plus 6 is 3. 3 plus 11 radical 2. So, in summary, simplify your radicals so they end up with the same radicand, or the number inside the radical, and then just add. And you can do the same thing with subtraction too. I'm not gonna do another adding one, but basically you just break it down, get them simplified, and then combine like terms. With subtraction, it's similar. I mean, we still have to simplify our radicals, so I'm going to simplify these. 45 is 9 and 5, which 9 is 3 and 3, so I have a pair of 3. So this becomes 8 minus 3 radical 5. That 5 is left over from there. Minus, I'll do 20, which is 4 and 5, which 4 goes to 2 and 2, which there's a pair of 2's. So this is negative 2 plus 2 radical 5, and that 5 is the leftover. So now that they have the same radical, I can combine these. The only difference with subtraction and what you've seen in previous lessons is this negative needs to be distributed. So it'll turn to a positive now, but now this is positive 2 and negative 2 radical 5. And now we can combine like terms. 8 and 2 make 10. And negative 3 radical 5 and negative 2 radical 5 is negative 5 radical 5. Okay? And so that's simplifying. And the same concept happens for number 4 too. Simplify your radicals, and then don't forget, if you have a minus sign in the middle, you will need to distribute that negative into there once you're done. I wouldn't try doing it before. I would do it at the end, once you're done simplifying. Multiplying, almost done here. Multiplying is a little easier because I don't have to worry about the radicals. When you're multiplying radicals, the radicals don't have to be the same. So the number that's inside the radical when you're multiplying doesn't actually have to be the same. You can multiply anyways. Because of our properties which we discussed in the previous page, when you multiply radicals that have the same root, you can just multiply what's inside the radicals. So similar to the way we did this before with when you were multiplying polynomials, remember that you have to do this sort of double distribution. I have to do this times this, this times this, this times this, this times this, and then combine like terms when you're done. So let's do that. First, 3 times negative 4. Okay, negative 12, that's pretty easy. 3 times 6 radical 5 will be 18 radical 5. Negative 5 radical 5 times negative 4 will be 20 radical 5. Just the numbers get multiplied there. Now here's the trick part. Okay. Negative 5 radical 5 times 6 radical 5. Remember your rules. The outside ones will multiply. So negative 5 times 6, that's easy. That's negative 30. But the radical 5 times the radical 5, remember, if they're the same root, you can just multiply what's inside the radical together. 5 times 5 would be 25. What's nice about that is now I know the square root of 25. Okay, 5 times 5 is, that's square root of 25 is 5. So this actually can go away, and it's just 5. Square root of 25 is 5. So then I can do that part, which is negative 30 times 5. So let's let's combine some like terms here. So I have negative 12. 18 plus 20 is 38 radical 5. And then I have this negative 30 times 5, which is negative 150. And then I can combine these to be negative 162 plus 38 radical 5. And so that would be simplifying with multiplication. So again, unlike adding and subtracting, you don't actually have to simplify the radicals. You just follow your rules for multiplying binomials here, and you have to do that double distribution. So we'll try another one. Double distribution here. 4 times 2 radical 3 is 8 radical 3. 4 times 5 is 20. Okay. Negative radical 3 times 2 radical 3 is negative 2 radical 3. And then, oh, sorry, I didn't even see. Sorry, negative radical 3 times 2 radical 3. Remember that what's inside the radicals can be multiplied, so that's not negative 2 radical 3. That's 3 times 3, which is 9. And then finally, negative radical 3 times 5 is negative 5 radical 3. Now, we're going to sort of clean things up a little bit. I have like terms right here and right here. I also have this radical 9. Square root of 9 is 3. So I can just do negative 2 times 3. So I'm going to clean this up a little bit. 8 radical 3 and negative 5 radical 3 is 3 radical 3. and then plus 20, and then I have negative 2 times 3, which is negative 6. Which turns out, and I like to write the numbers first and then the radicals, so I'm going to do this first, and then plus the 3, radical 3, though it doesn't really matter the order. And that's it. Okay. Last step, or the last thing here, is going to be dividing radicals. This is another thing that is going to be a new concept. We never dealt with radicals in the denominator. So technically, you cannot have square roots in a denominator. We cannot have a radical in the denominator. It's just not proper when writing things. So what we have to do is what's called rationalize the denominator. And what that means is we have to fix this denominator by multiplying by the same. So if we want to get rid of the square root in the denominator, what we do is we multiply the root by itself, or whatever would cancel out that root. So you do that with single radicals like this. They're easy to rationalize because you just multiply by the same thing, and you multiply by the top and the bottom. You can do that because the square root of 5 over the square root of 5 is just 1, so you can do this. But the whole point of doing that is that you actually get rid of the square root, because the square root of 5 times the square root of 5 is the square root of 25, which we know. And 3 times radical 5 is just 3 radical 5. The whole point of this is you get a radical that you actually can solve. So I know the square root of 25. It's 5. And now the radical is gone from the denominator, and you have an answer. So you can do that with single radicals. It's easy. You just multiply it by the same thing on the top and the bottom, and that'll give you a radical that you can. It'll give you a perfect square radical that you can do. Like this was 25, and then the answer is 5. When you have multiple things in the denominator, like with the radical, the way to get rid of the radical in the denominator is to what's called, and let's do it right here, multiply by the conjugate. Okay. Or, in parentheses, opposite sign of radical. So how that looks, so if I want to get rid of, and I'm gonna extend this out a little bit so I have room to do what I need to do. Move this out over here. Just do this over here. What you're wanting to do, and I give myself some room. What you're going to want to do is multiply by the same thing. So similar to this I just multiply by the same thing. But with this, you have to multiply the same thing, but the opposite sign of the radical. So unlike when it's just a radical, it's easy. You just multiply by the same thing. With a conjugate, when you have multiple things with a radical, in order to get rid of it, you have to multiply by the conjugate, which is multiply by the same thing, but the opposite sign of the radical. And so instead of 3 minus radical 2, we multiply by 3 plus radical 2 on the top and on the bottom. On the top part, you'll just distribute. So negative 14 times 3 is negative 42, and then negative 14 times radical 2 is negative 14 radical 2. But on the denominator, you have to do this times this, this times this, this times this, and this times this. Okay? So let's try that. First, 3 times 3 is 9. 3 times radical 2. Negative 2 times radical 3 is, negative radical 2 times 3 is negative 3 radical 2. Can you see why multiplying by the opposite sign is important? Notice what happens here. What's going to happen when I combine these? They're going to cancel out. That's the whole point. And why you multiply by the opposite sign there is to get your radicals to cancel out. Now, if I have one more thing to do. I have to do negative radical 2 times positive radical 2, and I get negative radical 4. Remember, you can multiply what's inside the radical. But that's okay because I know radical 4. So let's simplify this. We know that this is going to cancel, and I just have 9 minus the square root of 4, which the square root of 4 is 2. 9 minus 2. So what I have now is negative 42 minus 14 radical 2 on top. And on the bottom, I just have 9 minus 2, which is 7. And now technically, that is the right answer, but if you remember this when we did quadratic formula, you can simplify this because all of those are divisible by 7. If I divide them all by 7, I get negative 6 minus 2 radical 2 over 1, or just that. So I know there's a lot there. We started with finding domain and range, which you should have already known with radicals. We started with simplifying basic radicals and Q radicals and any index radicals, which was somewhat new, but the concept was not new. And then we talked about the properties to where if they have the same radical, you can multiply or divide within the radical. You may have known that, though that may have been new. Simplifying radicals by adding and subtracting and multiplying, dividing. You did do adding and subtracting in Algebra 1, so that should seem familiar, but multiplying and dividing would have been new. And that's it. If you have any questions, please let me know. Send me a message. Come to AL, before school, after school, anything. Thanks.